Do you have the graph? You didn't keep the graph, did you? Yeah. No. The part that you tore off?
Yeah.
You don't have it with you? Okay, I'll show everyone.
I have it.
Because you're supposed to take 1 over x. You just leave it exposed straight? I got it right now. Check. Don't rip it. It's my simple mistake. Yeah. Like this one? Like this one. I could have got that one right. You just got put. If I just put a blood. But I would have got that one right. In my head, I was gonna do it. I was gonna do it in my head, and I was like, oh, this is x, this is a, so I'm gonna do it negatively because this. But it's just done. And this I didn't know what I was doing.
All right, it's 1 o'clock. Let's get going. So the first exam is over. These are the grades. So I believe we had 20 students take the exam. Highest grade. Now this is remember I let y'all have a 5-point bonus if you stayed after the test and did that problem and did it correctly. You could get up to 5 points. I've not added that in. They're actually sitting over there for you to grab, but this is just the raw grades after I graded the test the other night. All right. So the highest grade was 100. And the average, it doesn't say the average here, but the average was a 75. This is passing right here, so you can see like how many students passed the test versus not passed the test, how many A's, B's, C's, D's, and F's we had. Like I said, class average was 75. So normally in math and statistics, the class average is represented as X bar. 75%, and then we have this thing called standard deviation, sigma, was 16%, which that number just tells you how far apart the grades were spread from the average. The bigger the standard deviation, the worse it is, because that means if you have a big standard deviation, that means you have a lot of people who know what's going on, and then you have a lot of people that don't know what's going on. You don't have much in the middle. So this is about normal. I see about 16% standard deviations, pretty much normal. If it gets above 20, that's a problem. Lowest I've ever seen is like 8. So everything seems pretty on par for what I expect. That average is actually, if you think about what an A, a B, a C, a D, and an F in college, what they are supposed to represent, right? A C means you're an average student. Now, nobody wants to be average, but that's what C means, right? You're average. And then B means you're above average, and then A would mean that you're above average, right? And then D is the opposite, right? So D is below average, and F is below average. So if the class average is C is anything between 70 and 79, right? So in the middle of that's about 75. So the middle of this is like 75, and that's what the class average was. So the average student here is average. I like to see that. I mean, well, I don't like to see it. I wish everyone would get A's, right? But, it is what it is, right? So, all right, so that's the grade distribution. I'll do this for each test, and I'll actually have exam 1 and exam 2 up there so you can see students if they went up or down. And in terms of the exam, there was a question, some people are asking me about the first, you know what, is this it? Yeah, this is it, okay. Some people were asking me about this problem, right, where is it? The one at the very end that you tore off. This one right here. Oh crap, I'm not gonna be able to rotate it easily. Why is that not letting me zoom? All right. Okay, so we're gonna have to look at it sideways. But it was the one, what was it? Asking about where this function is what? Fails to be differentiable, right? So when does a function fail to be differentiable? Anytime you have a corner or cusp, or a jump or a break in the graph, right? Or a vertical tangent. So anywhere where we have a break in the graph would be a problem. So here at -4, x is -4 would be a problem. Where else do we have a problem? -3 as well, because you have a jump, right? And then what about here at 0? Well, your function is not continuous, right? Don't you need continuity in order to be differentiable? So you would say at what? 0? Oh. I have a student looking for me. Yes?
You can click on the little arrow thing to flip it.
Does that flip it? Don't tell me that's that easy.
Yeah.
It flips everything? Oh, okay. I want... Oh, I didn't.
It's 13.
It's all right, I'll just flip it all.
Oh, wrong way.
Do it again.
You do one and you.
Yeah, I'll just do it twice. Oops. Did that do it? I don't have my glasses on. All right. Hold on a second. I have a student out here looking for me real quick. I told them to meet me here. Hey, hello. Are you my student?
No.
No?
She's Jenny Bishop's.
Okay. I have a student looking for me. They're trying to check out a calculator, but they should be coming here. All right. Okay, sorry about that. All right, so, and then over here at 2, we have a problem, right? Because you've got a break in the graph. And then at 4, you have a corner, right? So that's what I was looking at. Now, if somebody wants to argue with me, I will be willing to argue with you if you want to question the validity of 0, because the original function is not defined at 0, but you can't talk about differentiability of a function if it's not continuous at that point. So you have to have continuity for differentiability. Yes?
Also a corner if you would have filled in that dot.
Pardon me?
It's also a corner if you would have filled in that dot.
Yeah, even if you filled it in, it's like the straight line segment goes to something curved, so they come together. It's not like a sharp corner, but it is a corner. That's what I was looking for on that. Okay? Now, I don't plan on going through the whole test. That was one that you didn't have the graph for it, so I wanted to show it to you. If you have any questions about how I graded something, please meet with me in my office. Historically, I've changed grades before. Students have come in, they've said, oh, you took off here, and then I've said, okay, well, explain it to me, and, if you feel like you were unjustly graded, then come make an argument. Be happy to hear you out. Sometimes sometimes I'll just miss something, like you had the answer and I didn't see it. So if something looks off, just come visit with me. Okay, you all ready? Get down to business today. So today is a very important day, and remember I'm going to end class at probably around 3:55 because I've got that training I have to go to, all right? Sorry to disappoint you. All right, so today we're going to be talking about the most important rule when it comes to differentiation, and that's chain rule. Before we do it, though, I want us to get some kind of ancillary things out of the way. So if I give you this y equals f of x equals, let's go with sine x times, sine x times x cubed plus x. Yes?
What section?
2 point, well, we're going to be starting 2.5, but we're not, go ahead and put 2.5. Chain rule is what it's called. All right, so I want to get a couple of things established before we get into the chain rule. If I want you to give me the derivative of this, there's a bunch of different ways I could ask for it, right? I could say find y prime, right? That's one way I could ask. I could also say find f prime of x. That would mean the same thing, right? Those both mean the exact same thing. Find the derivative of that. I could say find dy dx. That means find the derivative, treating x like your independent variable. Y is the dependent variable, so this value depends on x. So we're differentiating the y value with respect to x. I like this notation, that's the Leibniz notation, because it comes from the idea that the derivative is a slope of a tangent line, right? And a slope of a tangent line, well, slope of any line is rise over run. And so if you think about dy over dx, back when we were looking at the graph of a function, remember we had the 2 points and we slid this one close to it? What we're really doing, if we get really close in there, is looking at a little right triangle. Let's zoom in. Okay, zoom in on that. You have this point, right triangle like this. And this right here is like your dy, and this is your dx. It's like your infinitesimal little tiny change in y. If x changes a little bit, how much does y change by? That ratio is a slope. All right, so that notation really illustrates the fact that you have a slope here, right? And what else could I write? I could write find, here's a different notation. We've seen it, d over dx, and then I could put here f of x, like that. That would mean the same thing. That means find the derivative treating x like your independent variable. Okay, find the derivative of what? Of the f function. Okay, so all those mean the same thing, right? I'm going to use different notation today. Yes?
What about f of a?
F of what?
Like if I've seen f prime of a, or is that?
Yeah, so f prime of a was back before we started to look at the derivative as a new function, right? We were just saying, what's the derivative at this point? So we were finding slope of the tangent line at this point a. And then after that, we said, hey, instead of doing it at values of a, let's call that value of a x, right?
We probably won't see that anymore.
We're not going to see f prime of a much anymore. Yeah. Okay, so that's all. This is all just notation, right? This is all just notation. Now, getting back to this problem, we have here the product of two functions. Do you all agree with that? Do you all see that there is a product between these two? We have this right here, sine of x, times, right? There's our multiplication right there, times x cubed plus x. I want you to compare that I want you to compare that to this other function. I'm still going to call it y, is f of x, to this. Okay, so the big difference between these two, it's a subtle thing, but it's big, right? This one is, I initially didn't write it with the parentheses, so I'm going to take parentheses away, I'm going to take the dot away. Okay, here, the x here is being plugged into the sign. So anything that gets plugged into a function is called its argument. So the argument of this sine function is the x, right? So you take the x, plug it in the sign, that's one function, then you're multiplying times this polynomial function. Product. This is not a product. What do we call that when you have a function that is being plugged into another function? Not multiplied, right? That's multiplication, this times this, but this is, what do we call it? When you have a function and you plug it into another function. You remember college algebra? No? Composition. This is composition. So this is composition. You might remember if I write this, f of g of x. Do you remember that Fogg, Goff thing? Yeah, no? Okay, that's composition. This right here is a product. In order for you to be successful in this next section, you must be able to tell the difference between products and compositions. So one way that I think, as in the beginning of learning this, the way that I think about it is that if I were to give you a value of x right now, right? Let's say I said plug in a number. If I tell you right here, plug in 2, you would do 2 right here, right? And then you take sine of that on your calculator and you get an answer, wouldn't you? Then you would plug in 2 into this and you get an answer here. And then you'd multiply the answers. So you can see the product there. Do you all see that? Where here, if I told you to plug in 2, what you would do is plug in 2 here, right? And you would get, what, 10 right? 2 cubed, 8 plus 2, 10. You get 10, and then you would, on your calculator, do sine of 10, right? Never in there are you doing something times something. You're doing something inside of something else, all right? So what we are interested in today is not the derivative of this, because we can do this from last class. We are interested in how you take derivative when you have composition, all right? And to do this, we have to have a new rule. It's called the chain rule, all right? So I haven't told you how we're going to do it. So let's do this problem, because we should be able to do this from last class. If I ask you to take derivative of this, we are going to look at that as a product right here. Call this your f function, your g, right? So who wants to tell me what the first piece of this is going to be? F prime. So what for us, that's what? Sine x derivative, right? So I'm going to write sine x, take its derivative, right? Then times g x cubed plus x, and then plus g prime. Take the derivative of the x cubed plus x, right? And then multiply that times sine x. Okay, that's what we learned last class. If anyone's just coming in, all the tests are up on that table. Anything I have to give back to you is up there. Right? And now we actually have to just take derivatives. So the derivative of sine of x is cosine of x times, and then x cubed plus x. And then the derivative of this is 3x squared plus 1, and then times sine x. And I have to have this in parentheses, don't I?
Yes.
Because it's two terms, right? And so you're going to multiply by sine. It's going to have to distribute through. Same with over here. Keep that in parentheses because the cosine would have to distribute through. And right there is our raw derivative. We're just going to leave it like that. All right? So that we learned last class. This right here, how do we do this, right? So look, I've been teaching calculus for a long time, all right? Long, long time. And good thing is, calculus has never changed. It's always the same, all right? And I've tried all sorts of different ways to get students to learn the chain rule, all right? And this is one of those things where some students are going to get it. It's going to be quick. They're going to understand it. And then other students are going to struggle and struggle and struggle and struggle. And a lot of it is because they don't see the composition. They keep confusing composition with products. And so the way I'm going to present this initially, this idea of this chain rule, is to just show it to you the way that a Calculus 2 student will do it. Like, I'm going to try it because a lot of people do pick it up quickly like this. But if you're struggling with what I'm presenting, I will present another way that's a little more tedious but easier to follow, I think. The problem with the easier to follow method is that you want to get rid of that as soon as you possibly can. Like you want to step it up to what I'm about to show you. All right? So here we go. You ready for the chain rule? I'm going to give you the rule. I'm not going to prove it. I could prove it, but we I think agreed last time I had proven the product rule. That was enough for us. So I'm going to just give you the chain rule. And there's several versions of the chain rule. I'm going to give you the one that appears on your formula sheet. Here's what it says. If you have a function, f, and inside of that you have some other function, g. That's kind of what we have right here, right? We have a function inside of another function. In this particular case, what would be the g function? X cubed plus x, right? X cubed plus x is being plugged into the f function, which would be the sine, right? So if we have this, and you want to find the derivative, here's what it's going to be. First thing you're going to do is you're going to take the derivative of the f function. And inside of that function, you're going to plug in the g function. Without the derivative on the g, all right? Now, that might be confusing people. Let me write the formula, and then we'll see it in action. Then the chain rule says you now then take that and multiply it by, now you just do the derivative of the g. And that formula right there is it. I mean, there's nothing more to the chain rule. That is it. So one way to look at this is that we are starting with this function here. This is what we'll refer to as the outer function. And then this one is the inner function, right? You have the outer and the inner function. In this particular case, this is our outer function, and this is our inner function, right? So, yes? You'll see that? So this first piece, I'm going to do this in words. I'm going to describe that piece in words to you. What you're doing here is you're taking the derivative of the outer function and evaluating it at g of x. In other words, you're going to take the derivative of the outer function, and inside of it, you're going to plug in the g function. That inner function gets plugged in. You'll have to see it in action, all right? This is quite simply the derivative, I'm just going to put DER, derivative of the inner function. The hardest part of this is this part, because this part's just the derivative of g. Can you all tell me the derivative of g here? 3x squared plus 1, right? That's the derivative of what's in here. That part's always the easy part. The hard part is that first part, all right? Okay, here we go. Let's try and do this problem. Right here. Okay, what is the derivative of this? Okay, so let's see. Let's call on somebody. Edgar.
Yes.
All right, Edgar, you're up. What's today, the 22nd? Edgar. All right, Edgar, what is the outer function? Sine, right? The sine function. Do you know what the derivative of the outer function is? What? Oh, sorry, cosine, right? So I'm supposed to take the derivative of the outer, which you said is cosine, and then I'm going to evaluate it at g, which means plug the g into that answer. So what would you have here? You said it was cosine x cubed plus x. There we go. So you've taken the derivative of the outer function, derivative of sine is cosine, and then into it you are plugging the g function. Now times, we're done with that part, right? Now times the derivative of the inner function, which is 3x squared plus 1. Do you think that's right? I'm messed up. Something's wrong. What's wrong? That's the most common mistake students make right there. I need this in parentheses. Okay, now everyone needs to understand why I need that in parentheses. All right, I'm going to give you a quick example underneath. If I ask you, what's 5 times 3 plus 1? What's that? 16, right? Now, what's this? 20. Those parentheses make a difference, don't they? You were supposed to take this and multiply times this. Now, if this turns out to be two things, then that thing has to multiply times both, which means this has to be in parentheses like that. Okay? All right, let me show you, I hate showing mistakes, but let me see, I'm going to put it above here so I don't have to erase. Let's say a student takes a quiz and they give me this answer. Okay, what did they not understand? The what? That's not this, right? See, what they did is they said, what's the derivative of sine? And they said, cosine x. Well, that's not what you're supposed to do. You're supposed to take derivative of the function, which is cosine of what, though? What are we saying? Evaluate it not at x, but at g. So you're not plugging... this is not plugging the g into that derivative. This is multiplying g times the derivative of x. So that's not right, okay? You'll see the difference between those two? Okay. All right. Now, I'm going to show you this another way. I'm going to do the same problem. I'm going to do it a slightly different way, all right? You like that? That's okay? I really like this way.
Is that the answer for cosine?
Yeah, cosine of x cubed plus x times, in parentheses, 3x squared plus 1.
And that would be,
That's it.
that's it?
That's your derivative. Yep. Okay, so I like to bring visual aids in here. All right, so here we go. We'll use this.
Sine of x is a composition.
What?
Sine of x is a composition.
Well, the sine function by itself, right? The sine, like you can't just write sine. That doesn't mean anything. You have to have something in it, right? So if I just put x in here, sine of x, you could look at that as composition if you want. It's x being plugged into sine, right? I'm not sure I understand your question.
Yeah, that's basically what I'm asking.
Okay, but not. We're gonna look at a bunch of examples today, and we're gonna see all different types of composition. This is one type of composition. It's a function inside of another function, right? Okay, let me try this this second way, all right? And the way I'm about to do it is the way I prefer to do it, all right? All right, here we go for the derivative. Outer function, inner function. I'm going to replace the inner function with this spray bottle. What's the derivative? What's the derivative of sine of a spray bottle? Cosine of a spray bottle, right? Okay, so let me write that down. Cosine of the spray bottle. But what's the spray bottle? X cubed plus x. That goes in here. Okay? Then times. Now I've done the sign, right? Now I uncover that and take derivative of that, which is 3x squared plus 1. Y'all are looking like y'all don't like that. That is exactly what we just did, but I worded it a different way, right? I just kind of worded it a different way. It's like you're ignoring what was inside and just treating it as just something, right? Taking the derivative of that. Right? Like if I ask you right now, what's the derivative of sine of x? What would you tell me? What's the derivative of this? You'd say cosine of x, right? That's what you'd say. So it's like I'm replacing all of that with x, but it's not really x, it's this, right? And so derivative of that is cosine of that. Boom. And then chain rule says, okay, one more thing. Tack on the derivative of what was in there. Let's do another problem. We got to do like probably 1,000 of these, all right? Formula is going to go away. I'll put the formula off screen here. F of g of x. If we want the derivative, we take derivative of f, we evaluate that at g, and then we multiply times the derivative of g. All right, there it is. Let's stick with sine. Yeah, we'll stick with sine. Let's do another one. Okay, y is equal to sine cubed x. Sine cubed x. Okay, the first thing that you have to notice here, or not notice, but you have to know, is what that notation means. This notation means sine x cubed. It does not mean sine of x cubed. Those are two different, these are different things, aren't they? The position of that cubed dictates what you're looking at. Having it cubed right here after the n and up here means you're cubing the sine function. Here, this notation means you're cubing the x, right? All right, so do you see a function inside of another function? Yes? What do you see? What do you see as the inner function? Sine x. And what do you see as the outer function? Something cubed, right? Something cubed. So the outer is this. I like to think of it this way. If I told you to plug in x right now, first thing that would happen is you would take sine of it, right? Like plug in 2. You would do that first. And then what would you do? Plug in 2, and then what would you do? Cube that answer, right? So the last thing you do is the outer function. The first thing you do is the inner function. All right, let's see if we can get this one. All right, this time I'm going to use my rag because my rag, it comes in handy because I can make it different sizes. Okay, I'm going to cover up the inner function with my rag. Or let's just go around the room. What's the derivative of a rag cubed? What rule are you going to use? Power rule, okay? Which means you're going to do what? Bring the 3 down. So it'll be 3 comes down, and then it'll be my rag, which I'm going to put a parentheses for, to the second power. Does everyone see that that's the derivative of the outer function? Yes? But I'm going to uncover the rag now and put that right in here. Okay, good. We're done with the cubed, right? The outer function's done. Now I say times. Now I look at the inner function. What's the derivative of the inner function? Cosine x, right? And I just tap it on right here. Tack it on. Boom. I'm done. You could rewrite it like this, just if you want to go back to the normal notation. You know, sine x squared really means this, right? There you go. That's your derivative.
You'll accept either of them?
Yeah, they're both equivalent. But if you look in the back of the book, they're going to have this. All right, here comes another one. Let's go ahead and do this one because they aren't the same, right? Those are not the same problems. All right, you know what? I'm not even going to attempt to learn names here. Umberto, since we talked earlier. Yes? Where are you? There you are. All right, do you see an inner function? What is it? X cubed. Okay, that's your inside. And then the outer one? Sine. Okay. Now, where do we always start? Inner or outer? Outer. Okay? Here we come. Here we go. There used to be erasers in here.
So do you always do the out first?
Always out first. Yes, always the outer first. Oh, there is an eraser right here. All right, Umberto. Perfect little size thing for you. I'm going to cover up the inner function, right? That's an eraser, Umberto. What's the derivative of sine of an eraser? Cosine of an eraser. Now, what was the eraser? X cubed. Okay, good. You want to keep going?
Sure.
Okay, now what?
So
Multiply that by,
3x squared.
so the derivative of that eraser. And that is technically done. Now, we could, and most of the time we do this, we like to move any numbers, constants, variables out in front and just leave it like that. That's not necessary, but again, most textbooks, they're going to move that out front. So far, is everyone okay on these?
So the g of x would be the outer.
No, g of x is inner. Inner, outer. So g and f. Okay? So before